Hi everybody, and welcome to tonight's video where we are going to be talking about quadratic inequalities. So far we've been talking a lot about quadratic functions, and we have been talking about how their graphs are the shape of a parabola. So what we're going to do now is take a look at those parabolas and see where they are either above or below the x-axis. This is going to be something that's going to interest us, especially just like we were interested in the vertex to find maximum and minimum. Similarly, if we were using quadratic models, it might be helpful to determine where they're above or below the x-axis, or in other words, where they are greater than 0 or less than 0. And we can also use our equal to inequalities. So we'll also see less than or equal to or greater than or equal to 0 as well. And if we do that, it includes the x-intercepts. Okay, so let's take a look. We got a couple examples right here of a couple parabolas. And so if I'm looking at this red parabola, it's in this region here that it's above the x-axis, right? So that's where the f of x values, the function values, the y coordinates, are all going to be positive or greater than 0. At these special points right here, the x-intercepts, that's where the value of f of x, or the value of the function, equals 0. And then down here, below the x-axis, all the y coordinates are less than 0, right? So this parabola, it's continuous, so there's going to be parts of it that are less than 0, parts of it that are equal to 0, and parts of it that are greater than 0. Okay? And so we're just going to want to be able to determine the intervals on which these things occur. So that's why it's going to be very important to identify the x-intercepts, which we already know how to do, and then be able to describe which interval it's either below 0 or above 0, or possibly including equal to 0 as well. So in this case, let's take a look at this and find out these values. So I have negative 1, 2, 3, 4. So it equals 0 at negative 4. Then 1, 2, 3, 4 over here. So my zeros, or my x-intercepts, are negative 4 and 4. So if this is, we'll call this f of x, I can say that f of x is greater than 0 on the interval. And remember, we're going to use interval notation. So our x coordinates, so it's greater than 0 in this region here between negative 4 and 4. So my interval notation looks like this. And I used parentheses just because I just had the strict inequality of greater than 0. I could also want to determine where f of x is greater than or equal to 0. And so in that case, that's where I would use brackets for negative 4, 4, because notice it's greater than or equal to, so I want to include the actual points where it equals 0. So that interval here, from negative 4 to 4 inclusive, is where it's greater than or equal to 0. Now, where f of x is less than 0, is actually split up into two intervals, right? Because all the way from here, from negative infinity up until I hit negative 4, it's going to be down here below the x-axis. Then it cuts above, and then over here it's again back below. So it's on the interval of negative infinity to negative 4. Just going to use parentheses because it's just a less than. And then we can union that with the other interval on which it is negative or below 0, which would be from 4 to positive infinity. And again, another way I could write this is f of x is less than or equal to 0. And if I did that, I would want to include those zeros with a bracket. So those intervals would be negative infinity to negative 4 bracket, union, bracket, 4 to positive infinity. And I'd use my parentheses there, okay? So take a minute and pause the video and for yourself determine where, if we're going to use, we'll call this one g of x, write out the intervals on which g of x is greater than 0, where it is greater than or equal to 0, where g of x is less than 0, and finally where g of x is less than or equal to 0. And then bring that with you to class tomorrow, and we'll start with an example explaining that. Okay, so you can pause the video, write this down, try it on your own, and then bring it to class. Okay, so we were talking about quadratic inequalities. We're gonna use our different inequality symbols. A lot of the time that we're gonna use these, we'll already have it in a form that looks like this. We'll have it just like a standard form of a quadratic function, ax squared plus bx plus c. But instead of equal to 0, we'll have one of our inequalities. So we could have less than 0, we could have greater than 0, less than or equal to, or greater than or equal to 0. Now, it's not always going to be where we have a 0 over here, and we'll do an example where it's not over there. So all we'll want to do is move everything over to this side of the inequality so that we do have 0, because then once we have it where the inequality, it looks like it's in standard form, and then it's got a 0 over on this side, then we can solve that either graphically or algebraically, which is what we'll do now. So let's say I have this quadratic inequality. Negative x squared plus 4 is less than or equal to 0. So what I want to do, I have 3 steps here to solving this graphically, and it's going to look just like those examples we did with the red and the blue parabola. So the first thing I want to do is graph the corresponding quadratic equation, right? So this is an inequality. An equation is just when we have an equal to, right? So the corresponding quadratic equation is negative x squared plus 4 equals 0. Okay, now there's a few different ways you could do this. You could graph this with Desmos, with your calculator, by hand, or just using kind of like our transformation facts. So negative 1, I know this opens down. It's just a regular parabola. It isn't vertically or horizontally stretched. And there's no h, so it doesn't shift left or right, but there's a plus 4, so it shifts up. So it opens down and shifts up 4 units. I picked 4 because conveniently, if I put my vertex at plus 4, when I draw this parabola that's opening down, it will intersect right here and here at a couple of nice numbers. And so now when I draw my parabola in, that looks like this. Okay, I'm going to graph my corresponding equation that looks like this now, and I'm going to identify and label the x-intercepts. So my x-intercept here is at the point negative 2, 0. So the x-intercept is negative 2. And over here, that's at the point 2, 0. So my x-intercept there is positive 2. So I identified and labeled the x-intercepts. You could label them as a point if you want, like so. But just recognize that the x values are negative 2 and 2. So that's important to do, because now we're going to go back to just like we did with that first example and determine the interval or intervals, remember, that could be separate, that satisfy the required inequality. So I want to find out now where this graph is less than or equal to 0. Okay, so it's less than or equal to 0 where it's below or equal to 0, right? So in this interval here and this interval here. So from negative infinity to negative 2, and I want the less than or equal to, so I'm going to put a bracket there. Now I'm going to union that with my other interval where it's less than or equal to 0. So from 2 to positive infinity. Okay, so that's the 3 steps that I would use here. Graph the corresponding equation, then identify and label the x-intercepts, because those will be the bounds of your intervals. And so we'll either be between them, basically, or on the outsides of them. So from negative infinity to negative 2, and then 2 to positive infinity. Our other solution probably, if we wanted to find out where this was greater than, it would have just been between negative 2 and 2. Okay, so those are 3 steps there to solving graphically. Sometimes they'll even just give you the graph, and all you have to do is jump right to step 3 and identify the intervals there. So that'll be a little bit easier. And then our last thing that we're going to talk about is if we wanted to solve this algebraically. So the first step we would do is solve the corresponding quadratic equation. So we have ax squared plus bx plus c equals 0, right? We'd want to solve that equation. And we can use 2 methods. We could either use the factoring method or the quadratic function, right? X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. That should be quadratic formula. I'm sorry, not quadratic function. So formula. So that's our other option, right? Or either factoring and then using the zero product property or the quadratic formula. Now remember, when we're solving a quadratic equation, we can get 0, 1, or 2 solutions depending on what the parabola looks like, right? 0 real solutions means that the parabola is like entirely above the x-axis or entirely below and doesn't cross it, so that would be just imaginary numbers. We get 1 solution if the vertex sits right on that x-axis, either opening up or down. And then we could also have 2 solutions if we have a parabola that either opens up and crosses in 2 points on the x-axis or opens down rather and crosses at 2 points as well. A lot of times, like we've seen so far in all the pictures that we've drawn in this video, we're going to have 2 solutions. So once we have the 2 solutions, those tell us where it equals 0. Now we got to determine if, along which interval it's either above or below, depending on what inequality we want to solve. So we'll have to test some points. So let's see what this looks like. We got an example here. 2x squared is less than x plus 10. I want to solve this. So the first thing that I want to do is I want to solve the corresponding quadratic equation. And remember, we always want that to equal 0, right? So like we said at the beginning, the standard form of this, we want it to have a 0 on one side of the inequality. So let's move some things over. So if I subtract x from both sides, I'd get 2x squared minus x is less than 10. Then let's subtract 10 from both sides, and we'll be left with 2x squared minus x minus 10 is less than 0. Okay, so solve the corresponding equation. So the corresponding quadratic equation would be 2x squared minus x minus 10 equals 0. So we said there's 2 options for this. I could factor this out and use the zero product property, or I could use the quadratic formula, right, where I identify a, b, and c, plug it in, and go from there. So I think I will do the factoring method here, right? So I'm going to factor this apart. I sometimes call this reverse foiling. So you want to figure out what 2 binomials you foil together to get this trinomial. So the first thing I like to do is you just kind of have to guess and check your way through. So 2x times x would give me the 2x squared, right? So I broke that apart there. Now I want to find factors that multiply up to negative 10, but when I combine them, when I do the outside and inside terms, they'll just give me a negative x. So what are my factors of 10, right? So I have 1 and 10 and 2 and 5, basically. So I'm either going to try to fit in a 1 and a 10 here, and 1 will be positive and 1 will be negative because it's got to be negative 10, or a 2 and a 5 to see how these figure out. Well, if I put a 10 here, I'd have 10, and then I'd have 2x. That wouldn't combine to be negative 1, right? So, and then if I did a 10 here, that would give me 20. That's too much. So I'm probably going to use the 5 and the 2. If I put 5 here, I'd get 10, and then I'd only have 2. So I'm going to try to put the 5 right here and the 2 right here. Now I got to figure out the signage because I want to get this to be negative x. If I put a negative here, I'd have negative 4x, and then here would be the positive. That'd be plus 5. So that'd be 5 minus 4, that'd be plus 1. So I have to put the negative right there and the plus right there so that I have 2x times x is 2x squared. Negative 5x plus 4x would give me negative 1x. And negative 5 times positive 2 would give me negative 10. Great. So now I use the zero product property, and I would get 2x minus 5 equals 0, and x plus 2 equals 0. And I solve these two equations separately. And so I would get x equals 5 halves, and then over here I get x equals negative 2. All right, so these are my two x-intercepts. So if I'm thinking about this graph, the parabola intercepts the x-axis at negative 2 and 5 halves. Now I got to figure out what that parabola looks like. And there's a couple things that I can do. One is I can determine how it opens from the value of a. This opens up, right? So if it opens up, that means between negative 2 and 5, so negative 2 and 5 halves, right? This parabola is opening up because a is positive. So that means it must look like this, right? It must somehow look like that. So I can go back to solving my inequality. I want to find out where it's less than 0. So it's going to be less than 0 between there. I always like to check a value that's in between negative 2 and 5 halves just to make sure it satisfies this inequality. So we know that between negative 2 and 5 halves, we get 0, right? Because this is negative, this is positive, so somehow it crosses over the y-axis. So 0 is an x value that has a point on this parabola. So let's plug in 0 here and see if it satisfies the inequality. So 2 times 0 squared minus 0 minus 10. So 0, 0 minus 10. So is negative 10 less than 0? Yeah, it is. So that means in this interval here, our parabola is less than 0. So now we want to answer our question, our inequality, using the appropriate interval. And so our final solution is that 2x squared less than x plus 10 is valid for the interval where x is between negative 2 and 5 halves, and we are not inclusive because it's just a less than, not a less than or equal to. So negative 2, comma, 5 halves, using parentheses here, is my solution interval. So the graph of the parabola would look something like this. That little red highlighted area is your solution interval, and this is your solution in interval notation, negative 2 to 5 halves. Okay, a bit of a long video, I apologize, but bring this example with you to class tomorrow. We'll do some practice problems, and I'll see you then. Have a great night.